All right. At this point, you should be seeing some data that we have over Frankfurt, Germany. This is our best scale data, and as you can see, it's actually pretty detailed. You can see we have pretty much every stoplight, every crosswalk, even every tree that's in this urban area of Frankfurt, Germany. Now, today I've been tasked to take this best scale data that we have and create a map at a scale of 1 to 50,000. So if we zoom out to about a scale of 1 to 50,000 and take a look at this data, you can see that there's really just way too much information here for us to cleanly depict it at that scale. And it's just too cluttered, right? And so we're going to leverage generalization tools and techniques like the ones that Mark described to automatically create data that's more appropriate for that scale. So if I drag this other window to the side here, you can now see data side by side. Let's zoom back into the urban area. And you can begin to see how some of our data has transformed. Now on the right, this is the result after we've run automated generalization techniques, but before we've done anything to make the data look pretty, right? The data's been symbolized, but you can see that there's still some features drawing on top of each other. That's expected. We'll talk about how to clean that up later. All right, so let's explore some of the ways that the data has changed. If I zoom in just a little bit more and start scrolling around a little bit, maybe pan to the side here, let's look at the roads, right? So you can see that there's a lot of roads in this particular area in the base data, and you can see that there's fewer roads in the generalization results. Now, part of that is using thinning techniques to remove the lesser important roads. So here you can see some orange roads. Those are a lower classification than the red roads. So you can see that those disappeared instead of the red roads in this area. But at the same time, we're maintaining the overall pattern of our road network as we do our generalization. So some of these key features in the road pattern remain. And so it's a combination of looking at the classification of the roads, the density and pattern of the roads that we use as we go through and thin them. Now, we haven't just worked on the roads in this area, we've also done some generalization of our buildings. So you can see every single black building footprint, pretty much every building in downtown Frankfurt has been collected in our base scale data. But again, that's too much information to depict at 1 to 50,000. So we made the decision for our purposes that we wanted to create a built up area and only keep key buildings that are within that built up area. So you can see a light gray polygon showing up in the background on this on the generalization result, and that's the built up area that we created. Within that built up area, you can still see some buildings, some of the key buildings, like in this case, the main train station in Frankfurt. Let's see what this building is. The embassy, some churches, some hospitals. So all of those important landmark or key features are kept, but we've created this built up area as well. Now, in addition to building and roads, we can also work with our more natural features. So if I jump over to an area outside of the downtown urban area, you can see that outside of Frankfurt, there are some agricultural areas. All of these yellow features are agricultural polygons, and all of the green are types of vegetation. Now, one of the things that we want to make sure of in our data set is that there are no overlaps or gaps between any of these types of features. When we zoom out again to something, this isn't even 1 to 50,000, but you can start to see that these symbols become sort of blurry and cluttered. So we want to get rid of all of the smaller features, but at the same time, we don't want to introduce any gaps. So some of the techniques that we use is if we were to get rid of this small vegetation, rather than just deleting it, we would convert it and add its geometry to some of the surrounding agriculture. You can see a similar sort of thing happening with our hydro and vegetation over here, right? In this case, in the base data, our river is wide enough that we want to depict it as a polygon, but it's too narrow to depict as a polygon in our output scale. So in our output, we've just depicted the center line. And if we turn off the hydro surface here, you could see that there would have been a gap in the vegetation. But again, rather than just deleting or hiding that hydro surface polygon, we've decided to use techniques to merge and fill in those areas of agriculture and vegetation rather than leaving those gaps. So all of those are different tools and techniques that we use to generalize our data. Now, how do we put that together into something that we actually leverage? As Mark described early on, we use a lot of geoprocessing in Python. And with geoprocessing, we have individual tools that perform different operations. Like this one, delineate built-up areas. That's the tool that we use to create those gray built-up area polygons. We've got other ones to simplify and smooth, and really dozens, if not hundreds, of geoprocessing tools that we can then combine together into a series of models. And those models control and have the orchestration information about how we manipulate our features as we go through the different scales. So you can see that we pull in different features and we perform different operations, and this model then tells us how to process our features. Now, once we've captured all of this information in a model, we can reuse it over and over again on different data sets that have the same schema. So if I jump over to a different pro map, you can see that we're looking at a different geographic area. In this case, it's Mount Desert Island, which is in Maine. The majority of the island is made up of Acadia National Park with a few small towns and campgrounds and those sorts of things. So it's a very different geographic type of area than Frankfurt that we were looking at before. If we zoom in a little bit, though, we can see that we've performed all of the same generalization techniques because we've run the same models. So in this area, which is a town called Bar Harbor, you can see that, again, when we take those buildings, we create the built-up areas. We keep only those important buildings, like a fire station. You can see that we thin out the road network, again, keeping the main patterns of the roads. But here you can also see some other things that we've done to our data. If you look at the coastline here and the ocean, because this is a coastal one area, you can see that as I simplify one of these features, the coastline or the ocean, I can maintain coincidence between the two. So all of these, again, are various generalization tools and techniques that we leverage to take our best scale data and produce something that's appropriate for scale. In this case, we built our models to produce an output product of 1 to 50,000, but you can use these same tools and techniques to produce data at any scale.